Welcome to our lecture on linear programming and applications. Today, we are going to learn how to formulate a transportation problem. This is a powerful mathematical tool used by major companies across the globe to minimize shipping costs and optimize their supply chains. By the end of this video, you will understand how to translate a real-world logistics challenge into a precise mathematical model. To begin, let us imagine you are baking cookies in two different kitchens and delivering them to three friends. Driving uses gas, which costs money. Your goal is to match the cookies you have with the friends who want them, spending the absolute minimum on gas. In mathematics, this is a transportation problem. We move a single product from multiple origins, called sources, to multiple destinations. Every source has a limited supply, and every destination has a specific demand. Our objective is to find the most cost-effective shipping routes while perfectly satisfying these limits. Now that we understand the overall goal, we must translate this real-world scenario into strict equations. We start by defining our variables, which are the unknown numbers we want to find. Let m represent the total number of sources and let n represent the total number of destinations. We use S sub I to represent the total supply available at a specific source and D sub j for the demand required at a specific destination. The cost to ship one single unit on a specific route is C sub ij. Finally, our decision variable, the actual amount we choose to ship on that route, is X sub ij. With our variables clearly defined, let us build our objective function. This is the mathematical formula representing our main goal, which is minimizing the total transportation cost, denoted by Z. We multiply the cost per unit, C sub ij, by the number of units shipped, X sub ij, to get the cost for one specific route. The double summation symbols mean we must calculate this cost for every single route and add them all together to get the grand total. If the shipping amount increases or if a route is more expensive, our total cost Z will also increase. This objective function is subject to strict rules, starting with what we call supply constraints. For any given source I, if we add up all the shipments going to every possible destination j, that total must exactly equal the supply S sub I available at that source. You cannot ship more than you have, and in a standard problem, you must empty your inventory completely. We must write one of these equations for every single source in our problem to ensure factories are used correctly according to their physical limits. Just as sources have physical limits, destinations have strict requirements, which we represent using demand constraints. For any given destination j, if we add up all the shipments arriving from every possible source I, that total must exactly equal the demand D sub j required at that destination. The destination must get exactly what it asked for, no more and no less, to guarantee that the customers are fully satisfied. We must write one of these equations for every single destination in our problem, ensuring the entire market demand is met without any shortages. To complete our mathematical model, we need two final logical rules. First is the non-negativity constraint, which states that X sub ij must be greater than or equal to 0. You can choose to ship 0 units if a route is too expensive, but you cannot ship a negative number of boxes on a truck. Second is the balanced condition. For the standard transportation problem to work perfectly, the grand total of all supply from all sources must exactly equal the grand total of all demand from all destinations. If you have 100 total units, your markets must demand exactly 100 total units. Before we solve a real problem, let us visualize the equations we just built. The diagram you see represents the transportation network. The sources on the left push their supply through the network, and the destinations on the right pull their demand. Every arrow connecting them represents a decision variable and carries a specific cost, showing all the possible routes we must evaluate to find the cheapest overall plan. Now that we have our visual map, let us look at a simple problem with two factories and two markets. Factory 1 has a supply of 40 units and Factory 2 has 60. Market 1 demands 50 units and Market 2 demands 50. Our first step is always to verify the balanced condition. The total supply is 40 plus 60, which equals 100. The total demand is 50 plus 50, which also equals 100. Since both totals match exactly, the problem is perfectly balanced. With the balance confirmed, we write our objective function. We multiply the specific shipping cost for each route by the unknown quantity that will travel on it. For example, $2 times x11. We add all four possible routes together to represent the total money spent, which we want to minimize. Next, we write the supply constraints. For Factory 1, shipments to Market 1 and Market 2 must exactly equal its 40 available units. Similarly, shipments out of Factory 2 must equal its 60 units. Finally, we write the demand constraints to ensure customers are satisfied. The amount arriving at Market 1 from both factories must exactly equal the 50 units it needs. Likewise, the total shipments arriving at Market 2 must equal its required demand of 50 units. Along with the rule that all variables must be greater than or equal to 0, our mathematical formulation for this problem is now complete. Let us formulate a slightly larger problem to solidify this. A company has 3 manufacturing plants with supplies of 100, 200 and 150 units. They ship to 2 distribution centers, demanding 250 and 200 units. We use the exact same strategy. First, we check the balance. The total supply from the 3 plants is 450 units. The total demand is also 450 units. The problem is balanced, so we can move forward. Because we have 3 plants and 2 centers, there are 6 possible shipping routes. Our objective function pairs each specific unit cost with its corresponding decision variable, creating an equation with 6 terms. Our goal is to find values that make z as small as possible. Next, we write the supply constraints. The total amount shipped from plant 1 must equal exactly 100 units. The total from plant 2 must equal exactly 200 units. We finish the supply side by restricting plant 3 to its 150 units. Then we write the demand constraints. The first distribution center receives shipments from all 3 plants, and their sum must exactly equal 250 units. The second center's incoming shipments must equal 200 units. Assuming all variables are non-negative, this completes our formulation. We have successfully translated a complex physical limit into a strict mathematical rule. To wrap up, formulating the transportation problem is a critical skill in modern business. We learned how to translate a real-world shipping scenario into a strict mathematical model. We defined an objective function to minimize total costs and applied supply and demand constraints to ensure factories do not overship and markets receive exactly what they need. By mastering this setup, you can create a perfect mathematical puzzle ready to be solved for maximum efficiency.